Welcome back. I'm really glad you stuck around to continue our discussion on the first law of thermodynamics. Last time we talked about systems. Also, we defined a closed system. This is where mass does not cross the boundary.
Hey, that's the dotted line thing, right?
Yes, we will use a dotted line to represent the boundary of our system. Once again, let's look at the first law for closed systems. I really hope you are uncomfortable with the number of times I have repeated the following phrase.
No,
No,
please,
not again.
In minus out equals change. For the next few episodes, why don't we focus on the left-hand side of this equation? The left-hand side represents the energy crossing the system boundary. And in a closed system, energy can cross the boundary as heat or work. Now, let's stop making heated air and get to work learning thermo.
Wow, you really just said that, didn't you?
For this episode, let's talk about work. You should have talked about work in your physics classes. Work is a type of mechanical energy based on motion. In the simplest form, work is the result of a force being applied over a distance. Most of you should be familiar with this equation, but this is only true if the force is constant. Here is a more general expression. Now again, I'm going to assume you've already had basic calculus, and you shouldn't panic when you see an integral sign. In a thermodynamics course, there are several types of work we may encounter. A few of these are the work stored in a spring, work done by an expanding gas, work from electricity, and work through a rotating shaft. Some of these may require that you compute an integral. Depending on your text and your instructor's preference, you may or may not encounter all of these. Now, if you have been reading your textbook, you have been reading your textbook, right?
I really try.
Yes, sir. Every
but the
day, sir.
material's kinda
And
dry,
sometimes twice
so
on
sometimes
Sunday.
It's hard to get through.
Right. Well, anyway, in your textbook, you may have noticed a dot above certain variables. The dot tells us the variable is measured per unit time. A W with a dot above it has a special name, power. Power is the rate of work. It indicates how much work is being done or transferred per unit time. Now, with that definition and bit of nomenclature out of the way, let's return to our discussion about different types of work. Again, there are 4 types of work we often encounter in a thermo class, but all of these derive from the more generic force applied through a distance. Again, this type of work should be familiar from physics, and you may have already seen electrical power in physics, electrical science, or some other course. If electrical power is new to you, let me introduce you. Electricity is the flow of electrons. One common way to generate electricity is through the use of chemical reactions. This occurs in devices like batteries and fuel cells. But here's what you really need to remember. Electrical power is the product of voltage and current.
Sir, I'm not familiar with these terms. What are voltage and current?
That's a fair question. If we oversimplify the concept of voltage, it is a measure of how hard electrons are driven to flow through the circuit. It's similar to pressure in a fluid flow system. The higher the voltage, the more likely electricity will flow. Current is a measure of the amount of electricity flowing.
So, I'm confused. Why are we using I for current and not C?
Well, I honestly don't know off the top of my head. We just do.
Okay, remind me again. How do we get from W dot to a regular W? Or is that important?
It is important. Again, power is work rate. So if we integrate power over time, we get work. If we have DC conditions, the voltage and current remain constant. Therefore, the integral to obtain work is rather simple. We find for DC conditions that work is equal to voltage times current times time. Now let's briefly discuss rotating shaft work. In most introductory thermo texts I've studied, shaft work is typically a value that is given to you. However, if you are given enough information, shaft work is fairly easy to estimate. You just need to know about the torque and the number of rotations, or the rate of rotation. Spring work is really just a specific type of force applied through a distance. This type of work can be estimated if we know the stiffness of the spring, also known as Hooke's law constant, and the distance the spring is compressed or elongated. When we talk about the first law, it is important that we distinguish between work going into a system and work going out of a system. When we deal with springs, we can easily observe this energy going in both directions. Notice when the spring expands into the system, the spring starts with stored energy and uses that energy to push the system out of its way. The spring is putting work into the system, thereby compressing the system. However, if the system expands and compresses the spring, this requires energy that was initially stored in the system to be transferred into the spring. Hopefully, this silly little graphic helps you understand a concept that is crucial for your understanding of thermo. When a closed system is compressed, work is put into the system. But when a closed system expands, work is done to the surroundings. This brings us to our final type of work, moving boundary work. Anytime the volume of a system changes, the boundary moves. This motion is the result of a force driving the boundary. This force is the result of pressure within the piston. Pressure is force per unit area.
Oh, sir, a force through a distance. That means work.
Exactly. When pressure causes the boundary to move, we call this boundary work. And since the product of area and distance is volume, we can integrate the pressure with respect to volume. If internal pressure causes the system to expand, this is boundary work out. And if external forces cause the system to compress, we call this boundary work in. In future episodes, we'll talk a little more in depth about heat, and also properties like pressure and internal energy. Hey, thanks for watching. Don't forget to follow us on Facebook, subscribe, check out our new blog. Stay tuned, there'll be more videos to come.